what is this? This is a function, ordinary mathematical function. The function is in mathematics operating on a point from set and yield other point in other sets. This is of course this is linear operator. We suppose it as linear operator. It's operator because it's functional limit functional operator because it's goes to a scalar field R. I need in this lecture to explain the concept of distribution, mathematical distribution. To understand distributions, we faced a new way of thinking about functions. This approach can seem very abstract at first, but the benefit is that we can generalize the concept of derivatives and of course use the concept of distribution to help you to solve the hard differential equations. I will focus on the theory, not on the applications. The new way is to think as a function. The new way of thinking of a function is to think of a function as operating on other function. This ordinary function f is operating on real number. It's take a real number and effect on it and yield a real number. It's this picture, x goes to f of x for L, x and R. Its effect on real number R and R belong to R. This is the picture of x in the range or the codomain. This is the ordinary definition of a function. The distribution is in this form. It's also a function, but the distribution is a function from sets to R. This set is the set of L functions, smooth functions, from R to R. The distribution T sub f is a function from set to R. This set is the set of L linear operators phi, which we will call test functions. I will study it more precisely in this lecture. Before that, I will in fact, here this distribution T sub f is effect on what? It's effect on a function. It's translate the function phi to, what is the picture here? The picture will T f of phi for L phi in this set. The distribution T sub f operating on phi, not on a number, on a function. The function in mathematics is a relationship between two sets. It's take elements of sets, elements, not other thing, elements of a set. This element is number, vector, and yield also a number or a vector. Here, the situation is different. I will take a function from the domain and yield a real number. I will take a smooth function, linear operator, and yield a real number. I will study the effect not on a number, not on a point. I will study the effect of the function on a function. The effect of a function on a function. To this reason, the name of distribution comes from the concept of it. The idea that the object distributes the effect over a function. not over a point. I mean, as I explained now, the distribution is effect on a function. Then it's distribute the effect not on points on L of, but on L of points. This is a function, Gaussian curve. This is Gaussian curve. This is Gaussian curve. I can study the effect here and yield a point here. This is independent variable, and this is dependent variable, and this is point. This is the function. The point, an element of the codomain. I mean, this is the ordinary function definition. The distribution is study the effect of the function on L points. Here, L points on the curve. I mean on the function. This is the function. This is the function. I call it phi. This the function phi of x. This phi of x. I will study the effect of distribution of a function on L of its points, not on special points, but in general function. This means that the distribution studies the general behavior of the function, not the general behavior of a function after we effect on it by this distribution. Now, the distribution defined by T f of phi equal to the integral from minus infinity to infinity of phi of x multiplying by f of x d of x. This is the formula of distribution. Let's take an independent variable, which is a smooth function from this domain, and put it in this integral. Why the formula of distribution is in this form, especially in this form? We say that we will study the behavior and distribution. The distribution in general studies the behavior of the function in L of its points, not in 1 point or 2 points, in L of its points. Then we effect on this smooth function phi by other function f. To this reason we write T sub f. This function f means that this function f describe the affection on the independent variable. It's called the kernel of distribution. In distribution, the integral goes from minus infinity to infinity. That's because we will study the general behavior in L of the plane, not in different points or special points, in L of the plane. So to this reason, we integrate the function this function from minus infinity to infinity, and we multiplying phi of x by f of x to operating on it. F of x is an effect on phi of x, is an effect on phi of x in L points from minus infinity to infinity. It's general. We will, as I say, we will study the general behavior in L points in the plane, not here or here or here. In L, the plane, from minus infinity to infinity. This integral is a real number. Then the result is a real number. Note that the distribution is linear operator. I will prove that now. From linear algebra, we know that the linear operator is firstly I will write the rule here. A function f is called linear operator if this rule is held firstly, this is the first equation, which is the first probability of the linear operators. F of x plus y is equal to f of x plus f of y. Secondly, f of lambda x is equal to lambda f of x for L lambda and lambda. This is the properties of linear map, not linear operator. The linear operator is a function from vector space, from a vector space to the scalar field of this vector space. The third condition is that this function f goes from vector space V to R. The three properties of linear map. Then f is linear operator. This is the three conditions. This three conditions is held in our distribution. The first one, for L, phi, and psi, and this set, the set of L smooth functions from R to R, we are called them test functions. For L, phi, and psi, and this domain, tau, t, and t, f of sub f of phi plus psi is equal to t of sub f of phi plus t sub f of psi. This is the first condition. The second condition, I not prove it yet. This is equal to what? This is equal to the integral of phi of x plus psi of x multiplying by f of x, and then here d of x. The integral is distribute over the addition from analysis. We know that. We know this fact. Then this equal to the integral from minus infinity to infinity of phi of x, f of x, d of x, plus the integral from minus infinity to infinity of psi of x, f of x, d of x. This equal to tau t of sub f of phi plus t sub f of psi. This is the first property is whole. The second property is t sub f of lambda of phi multiplying by phi equal to the integral to the lambda multiplying by the integral from minus infinity to infinity f of x, phi of x, d of x. This equal to lambda. It's clear. That's for L, lambda, and the scalar field R. This is the first two conditions of the linear operator. The third condition is held because the distribution is a function from this set to R. It's It maps its functions, its linear and its independent variables to R, to the scalar field R. Then the distribution is linear operator. I prove this fact here. Now, what is precisely the domain of distribution? What is this domain? What is the meaning of this domain? What is the natural or the properties of the functions of the function in this domain? In fact, definition. Phi is a function from R to R. Is called test function. And it is with addition to the properties. The phi is a linear operator from R to R. It's called test function with addition to to these properties. Two properties. The first property is phi is belong to C infinity of R. It's infinitely differentiable. The test function must be infinitely differentiable. It's belong to this the set of L infinitely differentiable functions and real numbers, real valued functions, infinitely differentiable real valued functions. This is the first condition. You must, before this lecture, study analysis, advanced analysis, and advanced topology and advanced linear algebra. The second condition is the support of phi is little than infinity. The cardinal of support of phi must be little than infinity. It's clear. I will explain it more precisely after I will write now these conditions. In fact, the test function, the second property, asserts that the test function must has a compact support. The compact support is bounded support and bounded support and a closed support. This is the first bounded support. This is the condition of boundedity, and SUP P of F is closed, must be closed. That the second condition explain that show that phi has compact support. This set here, phi of from R of L functions from R to R. We will denote it by this symbol D of R, or it's equal to this symbol. There is many symbols in different box. Infinity C of R. C to infinity of R means يعني shows the first condition. This small c shows the second condition, which means compact support, C compact support. This or other symbol, and if you can use any symbol of them. Then we can write other symbolization. T of T sub f, the distribution T sub f is a function from tau of R to R. I also define these two sets. The first set is the set of L functions phi from R to R, where the support of phi has finite members or finite elements, and the support is closed. That means phi must has a compact support. And the second condition here, I forget write it. Phi must be smooth. Phi also must be smooth. I.e., phi must be a member of C infinity of R, must be infinitely differentiable. This is the set of describe the domain of the distribution. This set is tau prime of R, or called tau dash of R, is equal to the set of L distributions from this set is describe the set of L distributions from the set of L distributions which them domain is this function, this set to R, where this is the formula. We defined it for LF from R to R. It's a voice.